Okay, so water potential. We're coming up on this topic here, and it's always a good one. Can be a little bit challenging, but we're gonna teach you how to do it, and you're gonna be fine. So, couple things before we actually get to the formula, because basically what we're gonna be doing is putting some math to osmosis and diffusion. Okay, so um, osmosis is affected by cell walls. So anything with a wall is not going to allow something to burst. So even though water's rushing in, if it has a wall, those walls are generally strong enough not to let them burst. But pressure then will build up, right? Because if stuff keeps going in and in this thing and it keeps going out, but a wall's holding it in, then pressure is going to be exerted back into that cell, okay? Which can then cause a change in the rate of osmosis. So the higher the pressure going this way, the harder it will be for something to come in. So the rate will then slow down, okay? So um, for the water potential, it's just like what it sounds like, the potential energy of water, right? So is water potential greater at the top of a waterfall or the bottom? Which way will it move? Well, that question's kind of the same as if you said, where's the greater where's the greater potential energy of a roller coaster if it's sitting at the top of the hill? It's kind of the same question, right? There's more potential at the top, and then once it goes down, then there's going to be less potential down there once it moves. Um, and so the function of water potential, um, water potential is really a function of two things: pressure potential and solute potential. Okay, these two things are going to be kind of what dictates water potential. So pressure potential, just like what we talk about here, the pressure against the cell wall, which we tend to call Turgor pressure. Okay, and when you're talking cell walls, you're not talking animal cells, right? You're talking plant cells, maybe bacterial cells, fungi cells, things that have cell walls. Okay, and then solute potential. This is going to just depend on the concentration of any solutes that are there, salts and sugars, ions, etc. So if we look at the solute potential here, solutes have a negative effect on water potential by binding water molecules. So you have to get used to the idea of free water. Okay, so there are water molecules, H2O molecules, okay, in water, obviously, but if there are solutes in there, sugars and salts, sometimes the waters are attaching to those other molecules in there, and so they're no longer free. There is less free water in there, okay? So, like this says here in the diagram, adding solutes to the right side of this YouTube diagram, okay, um, makes the water potential lower there. So if you add solutes, okay, it's going to lower the water potential, okay? And so this results in the net movement of water to the right arm because water will always move from a higher area to a lower area, okay? So at the bottom down here, water will move from an area of less solute, more free water, to an area of high solute, less free water. Okay, so you can look. The problem with this concept and these things is you always have you can turn yourself around very easily because are you talking about the water potential or are you talking about the solute potential or are you talking about free water? And some of those answers end up the opposite. So you kind of really have to hone in on what you're talking about and what angle you're kind of looking at this way. Okay, so if something has more solute in it, okay, then that is going to be a lower solute potential. Think of it this way: if you had a beaker of water and you had a salt shaker and you just put like that much salt in a beaker of water, right? And then you took a second beaker of water. You brought up a second beaker of water and you took the salt shaker and you went like that and you just kept putting salt in there. In fact, you took off the lid and you just poured it all in there and there's a ton of salt in there. Okay, between those two, which one would it be easier to get more salt into? Right? Well, the first one doesn't have very much at all, so it probably can take more salt and still dissolve and mix into the solution, where the other one is so concentrated you can't get more into it. Okay? So that's how you have to think about things as far as potential goes. Could I get more in there or not? Okay? So pressure potential, a little bit easier to think about. It's a positive pressure, so it's literally just applying pressure. Okay? And so on the left side here, If you put like a piston into that tube and you push down, that's going to create positive pressure, and so it's going to move the water up the other side of the tube. Okay, so at the bottom, positive pressure, high pressure potential will move water to an area of negative pressure or low pressure potential. You could also, on the right side diagram, have something over here. If you create negative pressure, then the water is going to move that way. You can think about the right side diagram as using like, the droppers we use in science class, where you go in and you suck things up, right? The little bulb droppers that we use. You squeeze it and then you put it in there and you let go. That creates negative pressure so that the solution moves up the tube. Okay, it's moving from high potential, like in the tube, to low because you created that negative and then moves up the tube. Okay. They can be opposing forces. Solutes and pressure can work, in opposite ways potentially. And so on this diagram here, you have a bunch of solutes on the right, which should make the water move to the right side, but you also have a piston there pushing pressure down, which should make the water move to the left. So in this case, they're just balanced and nothing's going anywhere because of them having these opposite effects on each other. If we look at a few plant cell diagrams here, and similar to the notes that we looked at the other day, where we looked at hypo, hyper, and isotonic, you guys can probably pick these out, especially by the size of the arrows in the pictures there, right? On the top one, you have a lot of water going in and not as much coming out, and it's swelling up, right? Things are getting pushed to the outside, so that's going to be hypotonic, hypo-hippo. And then, in the middle one here, you have a lot of water coming out, and that would be hypertonic. And then the one at the bottom is more even, that would be isotonic. Well, with plant cells, remember, we have these other words that we use. So pause the video if you want and try and figure out which one's which before I tell you. But yeah, try and see if you can sort out which one's which there. So hopefully you paused the video and you looked at this. So if the water's going in and it's creating a hypotonic and that's really creating pressure, that one's going to be turgid. Okay, the top one's going to be turgid, and you might relate that to the turgor pressure, right? That one's going to have a lot of turgor pressure because of all the water going in. It's going to create pressure in that cell. The one in the middle there, where the membrane is all pulled off the wall and it's all sucked into the middle and the organelles are all sucked into the middle, that's plasmolized. And then the one at the bottom that's isotonic, we just call flaccid. Okay? So here is our formula. Keep having to move my head around today on this set of notes. So here is the formula, and you see these things that look like tridents, right? And they look like Poseidon, Poseidon's tridents. And so you have water potential, which is the one on the left, is equal to pressure potential plus solute potential. And then it's written out in words there for you. And that's all nice, except for this one has our solute potential one right here has this whole mess that you have to pay attention to. So all of these things are going to create the solute potential, okay? So here's your solute potential, which is just one part of this formula. So this would be water potential, okay? So if you put a W there, this is water potential, pressure potential, and solute potential. And then solute has all of this to deal with. So if we come down here to the bottom, you can see that that negative I is the ionization constant, and really the negative doesn't really go with the I, it just goes in front of the equation. But the I is the ionization constant. How many ions in the water? So an example, salt, NaCl, would be 2, because if you watch the Bozeman video, it does a good job explaining this. When salt goes into water, the Na comes apart and the Cl comes apart, and they both occupy water. So there's 2 ions in there occupying the water. Whereas if it was sugar, C6H12O6, none of that actually comes apart in water, and so it only occupies water one time. All of those things don't occupy their own individual free waters. And so salt is 2. The ionization constant for salt is 2, and the ionization for sugar is 1. I will expect you to know those and memorize those. If it was anything else, then I would give it to you. But you should know salt and you should know sugar without me giving them to you. Okay? Molar concentration, how concentrated is the solution, is your C. The pressure constant is a constant. It's 0.0831 liter bars per mole Kelvin. okay? So a lot of times we just say bars, but that's just a constant, just a number that's in the formula. And then our temperature we deal with in Kelvin, and so typically we deal with 273 plus the Celsius temperature. So a lot of times you're giving the Celsius temperature in a problem. If you are, you have to add 273 to that. If you're given the Kelvin in a problem, then you should be good. This is just a plant cell diagram, and it just kind of gives you an example of what water potentials might be down there at the bottom. When you look at the solute potential and you look at the pressure potential, what the total water potential might be for a turgid cell, a plasmolyzed cell, and a flaccid cell. Really nothing to do here other than kind of look at the diagrams and look at the numbers, see if it makes sense to you a little bit. On this one, it kind of shows you why trees are able to get water all the way up to the top. Even though, like you guys all know, water soaks into the ground, right? Rain soaks into the ground. And even though a tree might be 30 or 40 feet tall and the leaves are wet, the water does not get absorbed into the leaves. That's not how the leaves get water. They get it all the way down here at the bottom. They get it all the way down here, right, from the soil, and it goes in through the roots and all the way up the trunk and up here, and then finally it gets, branched out up here, and we move it all the way through the tree. Okay, and so it comes up from the ground to the inside, but water has to fight gravity, right? Water's trying to go up, gravity's trying to push things down, so you have to be able to fight gravity and push water up this tree. Well, if you look at the numbers down here, here's a -2 down here in the soil, right? Your water potential down here is a -2. You have a -0.3 over on this side. And then here's your root xylem. Okay, xylem is one of the vessels in a plant that will move things. So you have xylem and phloem. Xylem moves water, phloem typically moves sugar. Okay, so the xylem has a slightly lower water potential. -6 is lower than -3. And then the trunk xylem is at 1.2, and the leaves are at -2, and then the outside air is typically at about -100. The MPa is megapascal, and megapascal is the same thing as bars. Okay, so what you can see is that you have to be also watch this because it's negative numbers, right? -2 is a greater number than -1.2. Okay, and so this would be high, and so the numbers are all going to I'm sorry, I said that backwards just a second ago. I looked at the wrong thing. I said -2 is a bigger number than -1.2. Not true. Ignore that. But I don't want to restart the video, so ignore that. Okay? Down here, the -0.3 is a bigger number than this, and this is a bigger number than this, and this is a bigger number than this. So the numbers are decreasing as you go up the tree, right? And so there's high water potential down here, and there's low up here, which is what's driving the water up the tree. Okay, and then you have really negative up here with the wind and everything up here really pulling water out of there, and that's kind of what's sucking the water up here in this direction also going up, and it's creating that little pathway, right? Because water transpires, we have transpiration up there, and so it's really just pulling it up the tree all the way along there, but a lot of that's due to the water potential. Okay, practice problems. So here's just a few problems I put in my notes, and you should definitely pause this video and look at these problems and sort them out. They are literally just kind of plug and play. These problems are just plug them in, plug and chug, put the numbers into the right part of the formula and solve for them. And then if you I'm not actually going to click to the next slide, which is the last slide, because it has the answers on it. So I'm going to make you do these problems, and then they will be, the PowerPoint is posted in there, so you can certainly go find the answers very easily if you want to, but plug them in, see what you can do, and these are very basic water potential problems. The ones I posted for practice get a lot more difficult. So we'll be having some WebExes early next week to kind of have you guys check in and see who's having problems, and we'll go through some of that next week, okay? But watch the Bozeman video. Hopefully, obviously, you're watching this video. Go do the practice problems as well, and then we'll touch base early next week on some water potential again, okay? All right, enjoy. Have a great weekend.